Okay, so in last class we have finished in the aldol condensation, and in the last class Gaurav raised the issues to discuss about the Wittig reaction. So in Wittig reaction, the main or the important parameter here is the formation of the C double bond to CH2. So in this case, some important reagent which is used, especially the ylide. So ylide means, this ylide is basically the combination of carbon atoms with different heteroatoms. Heteroatoms means it may be the phosphorus, it may be nitrogen, it may be sulfur, whatever it will be, the name will be accordingly varied. So in this case, generally for the Wittig reaction, the ylide what is used, that is the phosphylide. The general formula of the phosphylide is R3P plus CH2 minus. It may be CH2 or it may be Cr2. That means R3 plus R prime, R double prime minus. So this is the general formula of phosphylide. Now how the phosphylide is generated? I will show a specific example, especially triphenyl phosphylide. So in this case, how you will generate this ylide? You know that phosphorus contains the lone pair of electron, especially the triphenyl phosphine. So triphenyl phosphine is used, and another reagent is used, that is the methyl bromide. Now how the reaction proceed? Before starting with the Wittig reaction, triphenyl phosphine plus methyl bromide. This bromine acts as a leaving group. And this is the nucleophilic center. So in this case, if this is the leaving group and the nucleophilic center, as in the substitution reaction, you know this is delta minus, this is delta plus. So partial charge distribution is there, and if this is the partial positively charged center, then this nucleophilic center will attack here because it is electrophilic in nature, and simultaneously bromine leaves the molecule as a Br minus. So it will generate PH3 P plus CH3. Now after formation of this, and Br minus reside as an counter anion. Now after formation of this, to generate the ylide, that is the phosphylide, you have to use some strong base. The base here used generally N-butyl lithium. Okay, N-butyl lithium means N-bu minus plus Li plus. That means simple butyl group and lithium plus. So generally here butyl group or the butyl carbanion acts as a base, and the proton source is here the the CH3. So we can write it in presence of N-bu-Li, it will form CH2 minus plus LiBr plus NBuH. This is the simple reaction, and this one the target, that is the phosphylide, which will react in the Wittig reaction. This is the reagent that is produced by this OA. So this ylide is basically stable. Stable means not stable. Here the negative charge actually got stability with interaction with the phosphorus. So then you can write, as you know phosphorus is pentavalent, you can write like this way. So basically this is the charge distribution. We can write the resonance structure like this way. So during the reaction, this portion will act as a nucleophile. So when this is the nucleophile, you know in the carbonyl center, the carbonyl carbon acts as an electrophile. So here, if I take or write the reaction in the generalized way, that is the R1, R2, this is the carbonyl residue or the carbonyl derivative plus CH2 minus in presence of some solvent, dry solvent. Dry means that is the anhydrous condition. It will generate double bond CH2. So Wittig reaction is important for the transformation of C double bond to C double bond O to CC double bond. So that's why this is the importance of the reaction, of the Wittig reaction. Now what will be the mechanism for the Wittig reaction? In the Wittig reaction, as you know that this will act as a nucleophile and the carbonyl residue, that means C double bond O. This is the electrophilic center. Because in resonance structure we can show it, in the last class you know I have shown it, that means R prime O minus plus. So this center is electrophilic in nature and this is the nucleophilic center. So nucleophilic addition will take place. So this will attack here and the negative charge is localized on the oxygen. So here you will get CH2 CO minus R prime R2 PPH3 plus. This structure or this intermediate is named as the betaine. Now as we know, generally phosphorus has the good affinity with the oxygen. Another example of the good affinity with the oxygen is the silicon. Generally silicon, phosphorus, all these elements has a good affinity to form a bond with the oxygen. So here you can see that O minus, that means electron density, is now higher at the electronegative oxygen, and simultaneously the phosphorus, that is the phosphonium ion, is also adjacent with respect to this electronegative. So there will be the attack by this electron density to this electron deficient center, and it will generate this ring structure or this heterocyclic type of ring structure. Now it is the 4-membered ring, and name of this ring is the oxaphosphetane. It is the highly strained ring. So next step is the ring opening. Now why the ring opening takes place? First of all, it is the 4-membered ring, so that is the ring will try to release its strain. And the next thing is you know that the phosphorus oxygen is having the higher affinity of in between them. So there is the formation of the phosphorus oxygen single bond. Now if there is a chance of to form the phosphorus oxygen double bond, that means how many number of covalency is in covalent bond is increases in between the two elements, that will feasible in that pathway. So in this case you have to break the ring. Either this bonding electron will be shifted here to form the phosphorus oxygen double bond. So when it will be shifted here, it will generate plus minus, that means formation of the double bond here. Or you can write like this way. Say if I break this ring like this way in the stepwise manner, this is not a stepwise manner, this is a concerted way where the simultaneous this bond and this bond will be broken. But for your understanding I am showing like this way, as it is the electronegative atom, so this ring will, this bond will be broken and it will generate plus minus. Now next step is phosphorus has also again vacant orbital which can interact parallelly with this electron density or the electronegative oxygen. So that means it will again donate its electron here and simultaneously this bond will be broken. But for easy understanding you can also show like this way, in between phosphorus and oxygen it is the electropositive center. So I am writing like this way, say breaking of this bond and formation of the negative charge at this center now. So now this is minus plus, so this should be the plus, and it is just like of ylide type of structure, but this is not the phosphoylide because here already electronegative oxygen is present. So basically they will donate its electron and form this side product, and simultaneously there will be the formation of the carbon-carbon double bond. So this is the mechanistic pathway to form the C-C double bond from the C double bond O. Now in this case you need you will not show this mechanism by the stepwise manner, you have to do this concerted in the concerted pathway. So the mechanism will be like this way. After formation of the betaine, sorry, the oxaphosphetine, like pH3 after formation of this, either you can break this bond and then you have to revert back here, or you can break this bond, you have to revert back here. So this is the mechanism, and here you will get 4-membered cyclic transition state. This is the transition state of this state. So finally the product, here you will get double bond O plus R2. So the possible mechanistic pathway of the Wittig reaction. Now the question is why this ring will be broken. I have also answered this, because the phosphorus oxygen double bond is more stable and it also try to release its strain, and it is also mentioned in the given study material. So now after formation of the carbon-carbon double bond, here another question comes, that the stabilized ylide and the unstabilized, that is the normal ylide. Now what is stabilized ylide and what is the normal or unstabilized ylide? So in this example you have seen that this ylide is formed. Simple, this is a general not general formula, this is a simple example of the phosphoylide or simple ylide. In this case you can see that this negative charge can only form the double bond with the phosphorus, but this is not the resonance stabilizing. No electronic factor is involved here. So if some electronic factor is attached with this nucleophilic carbon, then the negative charge got stabilized, and then we call this ylide as the stabilized ylide. So as for example, like pH3 plus CH2 minus, say C double bond O OET, that is the ester group, that is the CO2ET. So in this case you can see that this negative charge got stabilized via resonance. So when this negative charge is got stabilized via resonance, then that ylide is named as the stable ylide or stabilized ylide. Now when the ylide is stabilized, there are now two cases. That means when no substituent is attached with this carbon, that means there is no substituent is attached with this carbon, then with reaction with the say acetone or say acetaldehyde, it will form this product. So in this case there is no question of cis trans isomerism, because here both the substituents is same, or EZ isomer. You know, E means that is the trans or anti, and Z means or Z means cis or syn. So when the cis and trans or the E and Z alkene appears, this question will appear when the ylide is the stabilized ylide and there will be the presence of substituent. That means first of all the E and Z, this term will not appear when the carbonyl is formaldehyde. There are no question of EZ isomerism, because here the substituents are same, and this ylide. Say the example double bond O plus, so this is your stabilized ylide, like PPH3 plus CH minus CO2ET, this is the stabilized ylide. But here you will get CO2ET, hydrogen, hydrogen. No question of the cis trans isomer, because these two are the same. Now if this is the phosphorylide, simple phosphorylide, you have seen the example that there is no question of the cis trans isomerism. So just keep in mind, if your substrate is formaldehyde and or the reagent is this type of ylide, then there is no question of the EZ isomerism. Okay. So next is how isomerism appear, or how you will show the EZ isomerism. So the example, like I am taking the example acetaldehyde plus pH3 CH minus CO2ET. This is the stabilized ylide. And another example is, this is one pathway, and another pathway is pH3 plus CH3 minus. Now you can see it that in this pathway, this ylide or this negative charge is stabilized via this electron withdrawing group. That means already you have seen this is possible via resonance. So when this is the stabilized ylide, so when the ylide is stabilized, then it will form the E-alkene, that means the trans alkene. So the structure of the product will be CH3 double bond CO2 ET hydrogen. Here you can see both the higher priority substituent is just anti with each other. So that's why it will form the E-alkene or the trans-alkene, okay, or the anti-product. Mind it, the ylide is stabilized, and here you will get this type of aldehyde or such a carbonyl. Now similarly, in this case you can see that this negative charge is not stabilized via resonance or via any electronic factor, and not only that, the presence of some methyl group, that is the plus I effect, is here. So it cannot stabilize the negative charge. So this ylide is not the stabilized ylide. So when the ylide is not stabilized, it will form the Z-alkene or the cis-alkene or the syn-alkene. CH3 hydrogen. So this is the difference between the stabilized ylide and the unstabilized or not stabilized ylide, that they can form two different type of isomers. So there are lots of examples, but if you want to remember this in the generalized way, then only path, that means in case of phosphorylide, if some electron withdrawing group having minus M effect, that means mesomeric effect or minus R effect, both are the same term, that is either mesomeric effect or resonance effect, both is present or attached with this negatively charged carbon, then the negative charge got stabilized and the ylide become stable ylide. So just keep in mind that some electron withdrawing group having minus M or minus R effect can stabilize the ylide, and they can form the E-alkene or the trans-alkene. But rest of the other, that means if some electron donating group or plus I containing group or non-resonating group is attached with this carbon center, having the negatively charged carbon center, then they have the no ability to stable this negative charge, and they can form the not stabilized, they can form the Z-alkene or Z-alkene or cis-alkene or syn-alkene. So this is the Wittig reaction as a whole. Now Gaurav, can you listen me?
Yes, sir.
Have you any doubt in Wittig reaction?
No, sir.
Clear?
Yes, sir.
Okay. So in last class, some of you have mentioned about the problem in the oxidation. So before starting with the oxidation, there are several oxidizing agents, but I mainly focused on the three oxidizing agents, especially the chromium reagent, the osmium reagent, as well as the KMnO4, that means the manganese reagent. Now in this case, first discussed about the chromium reagents. In chromium reagents, our target is to generally you know what is oxidation and reduction. Simple, the oxidation means the increasing of the oxidation number, that means increasing of the valence, and the reduction is the reducing of the charge or the reducing of the valency. So the oxidizing agent or oxidant, it has the ability, that means the oxidizing agent or oxidant can reduce its valency or reduce its oxidation number. Reduce its oxidation number. This is common for all oxidation or the redox reaction. So basically the oxidizing in oxidation reduction reaction or the redox reaction, the oxidizing agent or the oxidant itself got reduced, and simultaneously the other substrate or the other element got oxidized. That means they can enhance their oxidation number or can enhance their covalent number. And similarly for reduction, the scenario is just reverse, and reducing agent generally increases their oxidation number and the other element they got reduced. So in oxidation, the first, the chromium reagent which is used, here you can see chromium having the highest oxidation state, that is the +6, or you can write in Roman 6. In oxidation, that means in oxidation reaction of the chromium reagent, this oxidation state can be changed either to +3 or can +4. Okay. So here the example which I have been I have showed, that you can see the oxidation by using the chromium reagent, mainly the oxidation state has been changed from +6 to +4. Now there are several oxidizing agent or chromium reagent which can oxidize. Mainly we use the chromium reagent to oxidize the alcohol, and you know there are several alcohols like OH, primary, secondary and tertiary. But in chromium reagents there are few reagents which have no control over their oxidizing power, especially the chromic oxide, chromium trioxide or K2Cr2O7, potassium dichromate in concentrated sulfuric acid. They have no control over their oxidizing power. In this case, the alcohol, by using this oxidizing agent, it can be easily oxidized to aldehyde, but we can't isolate this aldehyde, we can't stop here. Simultaneously this aldehyde again oxidized to the corresponding acid. So that is the disadvantage of using such kind of oxidizing agent. But how the reaction proceed here, how oxidation takes place here? In the example, in the PDF you can see that there are 2-degree alcohol. This is the secondary alcohol or 2-degree alcohol. By using chromic acid, this is a controlled oxidizing agent in acetone, it can oxidize this 2-degree alcohol or isopropanol to the acetone. Now how the reaction proceed? The mechanism is like this way. So we can write the chromic acid like this way. Here you can see that the oxidation state of the chromium is +6. So it has the ability to reduce itself. This is the highest oxidation state of the chromium. So when you are using the 2-degree alcohol, so here oxidation state highest means it has a electron deficiency here. So it will try to accept the electron. The electron of the lone pair resides as the oxygen, it will attack to this chromium center, and simultaneously the negative charge is localized over this electronegative oxygen, so that it can generate chromium double bond O, O minus, OH. Now after formation of this is not a stable structure. Here it is easily removed from this system and will generate double bond O, OH plus, and here it will be the deprotonation step again from here. Now next step is the important step. Here still the oxidation state of the chromium is 6. So last step, that is the oxidation pathway. Here actually this carbon hydrogen bond will be broken, and simultaneously this bond electron will be localized here, so that the chromium become reduced, and the pi cloud is localized over this electronegative oxygen, and it will generate double bond O plus Cr, double bond O, O minus, OH, and this O minus is immediately protonated when it removes from the system. That means it will accept the proton actually from here, so that it can generate Cr double bond O, OH. Now here you can see the oxidation state of the chromium is reduced from +6 to +4, because it will contribute -1, and this is -2. So as a whole the molecule is neutral, so here oxidation state is +4. So this is the mechanistic pathway by using the chromium reagent, and it is acts as an oxidizing agent. Now there are several other chromium reagent which is used, especially the Jones reagent, the Collins reagent. The Jones, you need not to know the mechanism, but this is for your information, that Jones reagent, someone can ask you what is Jones reagent. Basically this is aqueous chromic acid plus acetone plus acetic acid or sulfuric acid. So this is the combination of the Jones reagent. Aqueous chromic acid in presence of acetone, in presence of either acetic acid or sulfuric acid. This reagent is named as the Jones reagent. So this is another oxidizing agent of secondary alcohol or 2-degree alcohol. Now other important agent is the Collins reagent. Just know the what is the reagent is used here. Here this condition is the anhydrous. That means here the acetone used as a solvent. Here the solvent which is used, that should or dry condition, that means no moisture will be present here, and this will be the solvent here used, that is dry dichloromethane, or in short DCM, and the reagent is used chromium trioxide in presence of dipyridine. So this is the Collins reagent in dry condition or anhydrous condition. This is important, and the reagent is used, that is the chromium trioxide in presence of dipyridine. So this is the example of the Collins reagent. But this Collins reagent or the Jones reagent, they have some disadvantage. That means this is basically the controlled oxidizing agent, but still they have the disadvantage. That means they are first of all costly, and you must have used in huge amount. So that is not the commercially viable. So to make the reaction commercially viable, or by using some controlled oxidizing agent, you know the name of that reagent already in class 12. The controlled example of the controlled oxidizing agent, two common name is there. One is the PCC and another one is the PDC. That means pyridinium chlorochromate and PDC is the pyridinium dichromate. So as a whole we can show the structure like this. So you know the structure of pyridine. This is basically acts as a base. So when this is protonated, this is the pyridinium salt, or we can write it PYH plus. So pyridinium, this is the pyridinium residue, pyridinium chlorochromate, CrO3 Cl minus. So basically the combination is pyridinium salt, pyridinium hydrochloride plus the chromium trioxide. Okay, so this is the PCC or the controlled oxidizing agent. That means say you want to convert to RCHO, you want to stop in the aldehyde step, or say you want to convert to the acetone, because you know upon oxidation of the both aldehyde and carbonyl, it will further proceed to the acid step, and by using the sodium dichromate, potassium dichromate in concentrated sulfuric acid or the chromium trioxide, it can be directly converted to the acid. You can't isolate this step. So that's why you have to using some controlled oxidizing agent, and the example is the pyridinium chlorochromate, which can restrict the reaction in this step. So this is the controlled oxidation pathway, and the structure of the pyridinium dichromate is, the activity of the both reagent is the same, but the difference is only in their composition. So in pyridinium dichromate, you know K2Cr2O7, this is potassium dichromate. So if we replace this potassium by pyridinium group, that means PyH plus whole twice, Py plus H whole twice and Cr2 2 minus. So this is the PDC, that means pyridinium dichromate, just like potassium dichromate. So it is pyridinium dichromate. So they both, the PCC and PDC, can act as a controlled oxidizing agent. So is there any doubt in the chromium reagent oxidation? Who have raised their issues in the last class? Any doubt in the chromium reagents oxidation? So if there is no doubt, then the other two important oxidizing agent is the osmium tetroxide and another reagent is the alkaline KMnO4. Why this two reagent is important? Because in this case, from alkene you can generate the diol derivative. That means the diol product, say R prime. And another important scenario of this two oxidizing agent is that both of, when you use this oxidizing agent to oxidize this carbon-carbon double bond to the diol, both the diol will be in the syn, that means they both will be in the same side. If I show the stereochemistry, say by using osmium tetroxide, it will form the syn diol. That means both the OH will be in the same side. Okay, so that is the importance of the reagent, and here you can see the mechanism that when you are using the osmium tetroxide, here osmium also is in the +8 oxidation state and it is got reduced to +6. When you are using the osmium tetroxide in alkene, it can generate the osmate ester. So this is basically the osmate ester. Now next step is the actually the oxidation pathway. Here you can see in the example that NMO generally used, that is N-methyl morpholino N oxide. This is the structure of morpholine. When I substitute this by methyl group, then this is named as the N-methyl morpholine. And what is N oxide bond? You know this. Say if they are NH2 group and I am using the peroxybenzoic acid, it will be converted to O minus N plus. So this is basically the N oxide. So by using peroxybenzoic acid, it will be easily converted to N oxide and N-methyl morpholino N oxide, that is named as the NMO. This is the synthetic pathway of the formation of the NMO from N-methyl morpholine. So what is the role of this NMO? This is acts as an co-oxidant. So that's why in the next step this bond will be cleaved and it can generate the diol residue, cis diol or the syn diol residue. So by using the NMO, it is the co-oxidant. You need not the mechanism, but the role of this NMO, it is acts as a co-oxidant so that this bond will be broken and it can generate the cis diol. So if anyone asks you or some transformation step, how you will transform from alkene to cis diol, then you can use the osmium tetroxide in presence of some co-oxidant. Now the utility of the KMnO4, alkaline KMnO4, it is also acts as an oxidizing agent and you will get again the syn alcohol. So the example, the important example is so this is basically cyclooctane. If I place a double bond here, that is the cyclooctene. So in this case, if I use alkaline KMnO4 and in the example you can see there is used Bu4N plus Cl minus tetrabutyl ammonium chloride. Basically this is acts as a phase transfer catalyst. And this is the aqueous alkaline KMnO4. So that can prepare OH. So again this is the oxidation and you will get the cis alcohol or syn diol. The using of this phase transfer catalyst is to transfer, that means this is your organic compound and you are using some organic solvent and this is the aqueous medium. So generally say this is the DCM, that is the heavier layer that will retain in the lower portion and this is the aqueous portion. Now this cyclooctadiene, it remains in the organic layer, it is totally immiscible to the aqueous layer, and this aqueous KMnO4, it remains in the aqueous layer. This is completely immiscible or insoluble in the organic layer. So how the reaction will proceed? That is the role of the phase transfer catalyst. If I draw the structure, actual structure of butyl lithium, plus Cl minus. Now here you can see both the hydrophobic character, that means non-polar part, you know that the butyl ring is the butyl chain is the non-polar chain or the hydrophobic chain. 4 butyl chain is remain here, and you can see here this is the charge part is also there. So we can write this molecule like this way. Say this is the polar head and this is the non-polar tail. Or we can say the non-polar as a term, this is lipophilic. And the polar as a hydrophilic. Philic or philia means love, that means it is aqueous tended, this polar part will be tended to the aqueous portion, and this non-polar part or the lipophilic part will be tended to the non-polar portion, that means at the organic layer. So you can see here this is the interface. So they retain in their interface. Now when they retain in their interface, this non-polar tail can interact with the cyclooctave in, and similarly this polar part can interact with this KMnO4 part. So in this interface both the substrate as well as reagent come contact to their each other and form the oxidation. So basically you need the phase transfer, that is the utility of the phase transfer catalyst in this reaction, that this reaction is proceed in their interface, that means at the junction of the both organic layer as well as the aqueous layer. In this interface both the substrate as well as your reagent come closer due to the presence of this phase transfer catalyst. That means somehow this phase transfer catalyst transfer this KMnO4 to the organic layer or the organic part to the aqueous layer. So this is the general role of the phase transfer catalyst in each and every reaction where it is used.